is recording. All right, excellent. All right, so I will just go over some basic things about cores and the Get Bankruptcy game, and then possibly the flow game. All right, so let's just go back to what the core is supposed to be. So if you have a cooperative game, a core is an outcome that is stable. Okay, so typically you would think of this as an outcome with the coalition structure, pi, so the way to partition the players into groups, and the payoff vector x, right? So you distribute the values of each group to each player, and you want to make sure that nobody wants to switch groups. Right? So you want to make sure that nobody switch groups. So to make sure that this happens, the way you pay out the players has to be more than, or at least as much as what they would get if they split off into a different group. Right, so this one is in the core. I guess I should do something first. Okay. Okay, this is in the core. If the value you assign to any arbitrary group, any arbitrary coalition, is at least the value of the group. Okay, so this is the value received by the group, people in that group, and this is the value that is that could be generated by that group. Right, so this means that there is no reason for any group to separate and try to get their own value, okay? Because they can only get up to this much. Right? So they can only get up to this much, but they are receiving at least as much as that. Okay, so there's no reason to deviate. Okay. So that's the definition of a core, right? So you want something to be stable. Okay. All right. And the bankruptcy game that we have is a convex game. And I don't think we need to remind you of what convex games are. Okay. But what we do know is that for convex games, it has a special property, right? So convex games always have a non-empty core. Okay, so not all the games, not all the cooperative games have a stable solution. Right? So it is possible that you have a cooperative game and there is nothing in the core. Right? So there is no stable solution. Okay, right? And we have a bunch of results from class through linear algebra, not linear algebra, linear programming. That gives you some characterization of when a game has a non-empty core or not. But for convex games, it's very easy. Convex games always have a non-empty core. Okay. Okay. All right. Now, one of the things about the core is this partition here, right? So this pi here. Right, so this pi partitions the players into different coalitions. Right, so in this coalition structure. Okay. But when you have a convex game, which is also superadditive, right, so that means the larger the group, the more value it generates. Typically, you will just think about the core in terms of only the grand coalition. Right, so if you have just the entire set of players as the coalition structures, that should usually generate the most value, okay, because of the superadditivity. Right? So larger ones generate more values. So typically, we just think about this as as the grand coalition in the coalition structure. Okay, so convex games always have a non-empty core, and it is superadditive. Right, so larger coalitions, larger coalitions have higher value. Okay, so it's super additive. So typically, we think of typically we only think about the grand collision. We only need to think about the grand collision. Uh, in the core. So we would have something like nx in the core rather than any other partition of the players. Okay, all right. So for such a game, we just pretty much just assume that the grand coalition is the coalition structure that we have. Okay. All right. And then the problem becomes, is there a payoff vector x, right? So is there a way to distribute the values to the players, right? So that the condition holds, right? So x of c is at least v of c. Okay, so the value received by each of the subsets is, well, the payoff received by each of the subsets is at least its value. Right, so we focus on x, where I guess we need to be a outcome that is efficient. Okay, that satisfies well, I guess I'll put a star here. This satisfies star. Okay, so we're just trying to find x where this is satisfied. Okay. All right. Okay, and the nice thing about convex games is that we actually do know what kind of x satisfies this the inequality here. Oh, what kind of x satisfies this inequality here? Okay, and that is through the marginal contribution of the players. Okay, so for convex games, okay, the marginal contributions will form an x that's in the core. Okay, so the marginal contributions will form an x in the core. Okay. Okay. Just a reminder of what marginal contributions is. We have a permutation. We order the players, right? So A1, A2, all the way to AN. Okay. So essentially, then we are looking at the marginal contribution of each of the players as we go along down the line. So x1, player one, would just be getting the value of just the first player minus the value of the empty set. Okay. X2 would be the value of the first two players, not x1, xa1, xa2. Okay, I should do this carefully. Xa1. So for the player in the first place, that's its marginal contribution. For the second place, this is its contribution. Right, so how much value does it add as you add the player onto the collision? Right, so that was the marginal contribution. Okay. All right. And the proof from class is saying that if you take any permutation of the players, look at the marginal contribution we calculate from that permutation, this vector we get is in the core. Right? So this is in the core. Okay. Okay. So right away, we get like n factorial possible vectors in the core. Some of them might be the same, but we get a bunch of vectors that are in the core. Okay. All right. Okay, so that's for convex games, right? So the marginal contributions will give you something that is in the core. Okay. But not only that, we can, as exercise, you can probably try to do. You can probably show that the vectors that are in the core is a convex set. Okay, so the set of all convex combination of these vectors, of any vectors in the core, is still in the core. Okay. All right. All right. And that just means that if you take two vectors in core, anything in between them is also in the core. Okay. Okay. Right. So and also so that means that the convex combination of all the marginal vectors, all the marginal contributions, would be all in the core. But in particular, we can also say that the core is precisely that set, and this is a harder proof that we are not going to be doing. Okay. Okay. So the set of convex combinations of all marginal contributions form exactly the set of vectors that are in the core of a convex scheme. Okay. All right. So that is that's a basic overall review. What the core is and what happens when you have a convex scheme. All right. Do you have any questions? I'll take a pause here and drink some water. Water is important. Okay. Apparently. All right. All right. Okay. So now we can talk about the bankruptcy game. All right. So for the bankruptcy game, somebody's bankrupt. Okay. So somebody's bankrupt and somebody owes M dollars. Or somebody owes M dollars to M players. Sorry, no, that's not right. Somebody somebody owes, someone owes, let's say D1 to DN dollars to players 1 to N. And so somebody's bankrupt, but they owe these N people these N values. Okay, but they only have M dollars, and we want to say, how do I distribute M to these players? Okay, so how to these players. Okay, so how do I distribute these M dollars to these players? Okay. Right. And well, I'll write down I'll make up a random example. Say somebody has $1,000 and they owe 4 people, and D1, D2, D3, D4. How much they, let's say 200, 500, 300, and 600. Okay. All right. Okay. So certainly the person owes more than what they have. So so we want to see how can we distribute these $1,000 to these 4 people who were owed these money. Okay. That's $600. Okay. All right. Okay. And the one formula we had, one possible formula we can use to make this happen is we look at any subset of the players. And so for any subset of the players, the value that they are going to imagine getting, okay, so the total value that they're getting is either 0 or it is the maximum amount. What is the, no, not the, it's either 0 or it is the maximum amount, which is m, minus what everybody else is getting. Okay, so sum I belongs to n minus s di. Okay. Sorry. Right. So in this bankruptcy game, the value of a specific player, specific group of players is, imagine that everybody else already got what they were owed, how much is left, and that is the amount that we will take. Okay, so it's a very generous formula here. There are other ways in making this formula, of course. Okay. All right. Okay. Okay. And using this formula, one can prove, and this is not easy to prove, but it is doable. You can prove that this is a convex game. Okay, so this is a convex game. Okay. Okay. So that's a convex game, and we're looking for some of the vectors that are in the core. Okay. And as we just said, the marginal contributions are in the core. Okay. All right. So let's try to see an example of a vector that is in the core. Right. So for example, let's arrange the players. So let's arrange the players. Let's say 3, 1, 4, 2. Right. So 3, 1, 4, 2. Okay. All right. All right. So let's start with the value of the player 3. Okay. All right. Right. So the value of player 3 has 300, but that doesn't matter. We're looking at the values, what the other people are owed. That's 700 plus 600. That's way more than 1,000. So that's 1,000. So it's basically 0. Right? Right. Because we have 200 plus 500 plus 600 is 1,300. And 1,000 minus 1,300 is less than 0, so we get 0. Okay. All right. And then the marginal contribution of 3, 1. Right, so 3, 1, these two are done. So the rest of them is 1,100. Right, so that is still 0. Right, that is still 0. Right, so 1,000 minus 1,100, that is negative, so that is still 0. Okay. All right, and then 314. Right, 314 is only 2 left. So the 2 is 500. So we get 1,000 minus 500. So that is 500. Okay. And when you get all of them, it is just 1,000. Okay. All right. Right, so these are the some of the values you get. Right. So when you have just the first one, just the second one, and just the third one, and just the fourth one. Okay. So then the marginal contribution, that would be for player 3, x3 is just v of 3 minus v of empty set, and that is 0. x2, no, that's not x2, x1. The second player here right? So that is going to be v of 3, 1 minus v of 3, and that is 0. And the third player, x4, v of 3, 1, 4 minus v of 3, 1. Okay, right, so now this is 500 minus 0, so that is 500. Okay. All right. And the last one, x2. x2 is just v of 3141, 42 minus v of 314. Yeah. And that is just 1000 minus 500. So that is 500. So my vector here is 0, 500, 0, 500. And that is a vector that is in the core. And so we look at the marginal contribution of each player, and we just calculate just calculate using the formula. So 1000 minus what the rest of them is, up to 0. Okay. And then we get the 4 values here, and that is the something that is guaranteed to be in the core. All right. And you can check that this is in the core using the definition. It's a little bit harder to check that this is in the core using the definition. You need to check that for each subset. You don't have the payoff for each for the players in that subset has to be at least the value of that group. All right, so that is the marginal contribution, and these are so there's one possible vector that is in the core in the bankruptcy game. All right. Okay. Okay. And you can do this for all the 4 factorial 24 permutations. Each of them will generate a vector using the marginal contributions. And any convex combination of those would also be in the core. In fact, the convex combination of all of them would be the set of all the vectors that are in the core. All right. Okay, so that is it for the core of the bankruptcy game, which is a convex game. All right. Okay. Any questions? We're all good? All right, so let's try something risky here. Let's try the flow games. Okay. Okay, so this is something related to network flows. So if you have done network flows before, this will be easier to understand. But if you don't know network flow, I'll try to make a very quick introduction to this. Hopefully you'll understand this quickly. Okay, right. So in the flow game, you have a flow problem. Okay? So what is a flow problem? Okay. Okay. So a flow problem is done on a directed graph. Okay, so graph with directions. In fact, I'll draw a directed graph somewhere in here. Yeah. All right. Let's do that. So that's a directed graph. It's a graph, but there are directions on the edges, and we call these arcs. Okay. All right. We have a source, which is S. Usually we'll denote that by S. That's where so we'll imagine the flow. So that's where all the flow comes from. Okay. We have a sink, not a sink, a sink, T. That's where all the flow will go to. Okay. Okay. And we have capacities. capacities on cities on the arcs. All right, so this is what it might look like. Let me use a pink thing to represent capacities. Okay. All right. All right. So one way to imagine this is to say that this is a network of pipes. So maybe you're sending water through the pipes. Maybe you're sending natural gas through the pipes in Europe, something like that. Okay. And each pipe will have a capacity. So that means the highest amount of water or natural gas you can send through that pipe. Right, so you can send up to 3 through this pipe, up to 1 in this pipe, send up to 5 in this pipe, etc., etc. Okay, so that is the setup for a flow problem. Okay. Okay. So that's a problem, but what is a flow? Okay, what is a flow? Okay. So flow is we send something. Well, we send flow, which is water or natural gas in our example, through each arc. So through each pipe. Okay, and there are some rules to this, right? So so to each arc and going from, oops. S to T. Okay. Right. So the way we're imagining it is we're sending the flow from the source S. So we're sending things out of S and we're trying to get the flow into T. Okay. So for example, I could say, let's send a flow of 2 out of here. So maybe I'll send the flows here from S to here. Okay. Right. Now, if you have a water that goes in to a place, right? So a flow, let's say 2 liters of water. That's not. No, okay. Suppose I send a flow into here. The 2 must come out somewhere. Okay. So in this case, it might come out of here or it might come out of there. So maybe I'll say I'll split it so that, oh, that's the wrong color. So that I'll have 1 come out of the first arc here and 1 come out of the second arc here. Okay, so basically anything that goes in has to come out until it reaches T. Okay, so this one here, maybe I'll send it through here. And this flow here, I'll send it through this arc and then this arc. Okay, so that is this arc, this arc. Okay, right, so flow, so for other nodes, flow in is equal to flow out. Okay. All right. All right, so that is a flow. Okay. Okay, so you're sending water from S to T, sending as much as possible. Okay. This is not the maximum you can send it through, but we'll just leave that here for now. Okay. All right. All right. And the value of a flow value of flow is the, I guess I should underline the flow like that. So the value of a flow is the total amount sent to T. Okay, so the total amount that is sent to T, or in this case, it is 2 in this example. Okay, I have sent a flow of 2 into T, right? So there's 1 coming in here and 1 coming from there. Right, so that is the value of the flow. Right? So certainly the more flow, so the more I can send, the higher the value it is, the better it is, right? So the more, the better. Okay. Right, so that is the flow problem. So that is a flow problem. Right? So if you have taken other optimization courses, so you might have seen this, but hopefully this is understandable to everybody. Okay. All right, any questions so far? Okay. All right. So that's a flow problem, but how do I turn it into a game? So how do I turn the game into a game? So here's is the flow game. Okay. We have some players and all right. And each of them will own certain pipes, or they will own certain arcs on this network, right? So each of them owns certain arcs. Okay, right. So maybe so for example, oops, let's paste it, shrink it. Uh, so for example, I could have something like one player owns these three, right? So maybe player one owns these three arcs. Maybe I have player two owns these three arcs. Okay, so they control these arcs here. So these pipes are in their control. And player three may be the rest of them. Okay, so player three is owns those three arcs there. Okay. Okay. So these are the players, and these are the arcs they own. Okay. So we're trying to set up a cooperative game here, right? So I have my flow problem that's outside of so that's the preliminary setup. And we have players, they each own certain arcs, so they control these arcs. Okay. Okay. Right. So now we have to define what is the value of a group of players, right? So for any group of players S, subset N, the value of S is the amount of flow, the maximum amount of flow we can send using only arcs owned by players in S. Okay, so for any subset of players, the value of that subset is the maximum amount of flow we can send using only the arcs owned by these players. Okay, all right. All right, so let's look at our example here. Let's paste this example again. Maybe not. Okay, so in our example here, if I just have the empty one, if no players in there, so certainly we can send nothing. Okay. If we look at the individual players in this game here, so if we just look at arcs in player one, there's nothing that connects S to T, so that will give you nothing. Same with player two, and same with player three. Okay, so if we just have one player here, it's going to give you nothing. Okay. All right. Okay. But what if we have players 1 and 2? Right, so players 1 and 2, what arcs they own? They own this. Okay, they own these arcs. Okay, so they own these arcs. All right. The maximum amount of flow I can send through this, well, I can send through here, and then I get stuck. I cannot send it out here. So that is still 0. So that is still 0. So 1 and 2, the value is still 0. Okay. But if we go to 1 and 3, right, things could be a little bit different. Right, so 1 and 3 have these 3 arcs and these 2 arcs here. Okay, these 2 are kind of sent into nowhere if you only think, well, I guess, yeah, there's these 3 and these 3. Right. So the only thing I can see is sending a flow of 1 on that path here. Right, so that value is 1. Okay. All right. And the value of 2 and 3. Right, so 2 and 3 is these 2, these 3, and this one. Okay. I can imagine sending flow 2 here, 2 here, and then 2 there. And I cannot send any more than 2. Right, so that value is 2. Okay. All right. Okay. And finally, the value of 1, 2, 3. This is slightly trickier. So you just look at the entire diagram, right? So if you look at the entire diagram, it is possible to send a flow of 4, right? So I will draw that here. Can I send a flow of 4 somewhere? I guess I'll send this one there. I can send one more here. I can send one more here, through here, and then I can send one more from here to here and to there. Okay. Okay, and that is the maximum. So this is the maximum possible flow I can get. Okay, so yeah, so that is the maximum possible flow. I can send up to 4 from S to D. All right. Okay. All right. Okay, so so here is the value of the grand coalition. Right, so we can send a flow of 4. Right, so if we send a flow of 4, maybe I send a 4 units of natural gas, then I would get the profit for sending 4 units of natural gas. Okay. Right. But then how do I distribute the profit we get from these 4 to the 3 players? Right, so 1, 2, and 3. Okay, so how do I distribute them to the 3 players? Okay. We're looking for something that is in the core, right? So something uh, that will make sure that they actually are happy with what they do, and they will not break off on their own. Okay. All right. Okay. All right. Okay. So, so this is not necessarily a convex game, but it's certainly super additive. So we just need to look at the coalition, the grand coalition. Right, so core with the grand coalition. Okay. All right. Okay. All right, so we can send the flow of 4 through this entire diagram, but how can I distribute the profit of these 4 to the 3 players? Okay. So that depends on how much each of them would typically contribute to the 4. If you just add up the amount that they have through each of their arcs, in this best possible flow, it's not going to add up to 4. It's going to add up something to more than 4. Okay. So the main idea then is to use something called the max flow min cut theorem. Okay. Right, so the max flow min cut theorem. Okay. Right. So I'll briefly tell you what a cut is. Okay. So a cut is something like this, where you separate S from T. You have things in here, and you look at the arcs that goes from the left to the right. So maybe that's 3, 4, 5. Okay. All right. Okay, so this is something that separates S from T, and you have arcs going from one side to the other side. Okay. Okay. All right. So in this case, I have a cut of capacity, 3 plus 4 plus 5, which is 12. Okay. Okay. All right. And the idea of a cut is that you can send at most this amount from S to T, right? So it's kind of limits how much you can send from one side to the other. Okay. All right, so this limits the amount we can send from S to T. So that gives you an upper bound on the amount you can send from S to T, amount of flow we can send from S to T. Okay. All right. And the maximum min cut theorem is telling us that the maximum amount of flow we can get is equal to the minimum capacity of a cut. Okay, so if you find a minimum cut, then that means that you can find the maximum flow of the same value. Okay, so that is the maximum min cut theorem. Any cut from S to T, it limits the amount we can send from S to T. And what we do here is to say that if we can find something that's minimum, then that is going to be the limiting factor. So that's going to be equal to the value of the maximum flow. Okay. All right. Okay, so in our example here, for example, if I look at this cut here, it has capacity 3 and 2. So this is capacity 5. Okay. But if we look at this cut here, this has capacity 1, 2, and 1. So this has max capacity. This is capacity 4. This is capacity 4. Okay. Okay. And capacity 4 equals to our value of our flow, which is 4. So that means that this is a min cut. Okay. Okay. So it's a bottleneck essentially, right? So this is a bottleneck. I can send as much. In this case, I can send up to 4 because of this cut, but I can actually send 4. So that's the maximum we can get. Okay. Ooh, can I do this in 4 minutes? I can do this in 4 minutes. Right. So here's the punchline here, right? So let's copy this down. Okay. And so here's the punchline. Right. A vector in the core is the following. Right. We look at a minimum cut. Right. So we look at a minimum cut, which has the value of the maximum flow, the value of the entire of the grand coalition. Okay, so and what we have is that we will give each player the amount equal to the capacities of the arcs in the cut that is owned by them. Okay, so the vector in the core is we look at the minimum cut, and for each player, we give them the amount that is equal to the capacities of the arcs in the cut owned by them. Okay. All right. All right. So let's have a look at this thing here. Okay. I'll erase some of these later. All right. So the minimum cut here. All right. So this is a minimum cut. Okay. Right. And we see that player one owns one arc here, which is this one. Okay. And that has capacity 1. So this player receives 1. Oops. Okay. The second player here actually owns 2 of these arcs, 2 and 1. So the second player here is going to receive 3. Right? And the last player here, the third player, has nothing in the cut. So they will receive 0. Okay, so they will receive 0. Okay. All right. And the idea is that this will be something that is in the core. And so that would be something in the core. I distribute the profits of these 4 to these 3 players according to the arcs that they own in the cut. Okay. And the reason for doing that is because this is the bottleneck. So these are the most important arcs that are in the network, right? Without these arcs, the network will not produce that as much flow. Okay, so that's why the players who own these arcs will get the payouts from the network, from the value of the group or the grand coalition. Okay, all right. And we will, because I ran out of time, I'll leave the proof that this is in the core to you to do as a fun exercise to do at home. Okay. And that is because we are right at 9:50. All right, good. Any questions? All right, I'll stop recording.